Welcome back, everybody. So today, I'm going to continue this discussion about the Lagrangian formalism. We are going to look at examples and how we can apply it and why it's so useful. And as we mentioned on Monday and also last week, this forms as a kind of stepping stone towards more advanced courses in physics. You're going to encounter many of these things again and again. And one of the advantages here is that we can actually start with the kinetic and potential energies. Instead of analyzing the forces and setting them up, we're actually going to set up the energies, and then from the energies, we will derive the equations of motions. At the end, this is in a way, it's not, how to say, a kind of free lunch thing, because at the end, we actually have to solve the equations of motions. Like we did in the second midterm and the first midterm, we actually have to solve Newton's equations. That's a very elegant way of deriving many properties. And last Monday, we saw that we could derive these Euler-Lagrange equations using what we call variational calculus. And today we're going to start with some examples. And the first example we are going to apply this to is to show that the shortest distance between 2 points is actually a straight line. So let's try to show you that. And then we're also going to use the Lagrange formalism to derive, or the Lagrangian, or the variational calculus, as we've been calling it. We're also going to use that to show energy conservation. And then gradually, we are going to bring in more, how to say, mathematical complexity. And one of the other things which we are going to start looking at is constrained motion. And that leads to a mathematical formalism, which is also very elegant. So you could think of finding the minimum of a function given some specific constraints. And you may have encountered something which are called Lagrangian multipliers, something like that in mathematics courses. That's a very powerful technique which allows us to solve equations with a constraint. So a typical problem we are going to look at is an object which is sliding down on a plane. So that's a type of constrained motion. And from the constraint and the potential energy and the kinetic energy, we're going to find the proper equations of motions. So it's a very kind of very nice overarching way of looking at a physics problem. So let's dive into the whiteboard and look at some of these technicalities and as a follow-up of what we did on Monday. I also wanted to just mention that on Friday, I will sneak in some 10 minutes of lecture, and then we're going to work on the homework 9. There will be an additional homework 10 for those of you who would like to have some extra points. The deadline for homework 9 is April 28th, and the final project is going to be presented on Friday, the 29th, the last day of the semester. I think that's supposed to be the last day of the semester. I need to check actually, because last year we actually ended lectures before the last day of the semester. Okay, so let's, if you have any questions about practicalities, the way we proceed. So let me just jump into the whiteboard and then do some of the basic mathematics which we need to do. And today we have Julie online, and she will answer those of you who have questions. And George, unfortunately, he actually got COVID. So, okay. So the thing which we defined on Monday is what we called for the action. And this is the quantity which we want to optimize so that we find an optimal path. And this quantity here is something we call for S. And we were integrating from a time t1. It doesn't need to be time. It could be a position x1 to a final position x2. And then we had an object. So everything which can be expressed in terms of an integral is something which often lends itself for variational calculus. So just to remind you of that, variational calculus deals with finding minima or maxima of a quantity which can be expressed as an integral. one of the quantities we are going to meet again when you look at more advanced physics courses is the energy of a system. That is often expressed as an integral. So if you want to optimize, find the energy minimum, that means that you're going to deal with variational calculus as a way to find the optimal energy. So this quantity which we have, this Lagrangian, it doesn't need to be the Lagrangian, it could be just a given function, as we will see now. So this function here, which we call the Lagrangian, is normally defined as the kinetic energy minus the potential energy. And I'm not specifying any kind of dependence on these objects. So one term is given by the velocity, and the other one is determined normally by the position itself. Now, what we ended up with on Monday was to derive the so-called Euler-Lagrange equation when we wanted to optimize this specific function S. And that led to equations where we have the derivative of this quantity with respect to x. And this quantity here is the velocity in our case, minus the time derivative, d dt, of dl, is the partial derivative of this Lagrangian with respect to the velocity. And these are called the Euler-Lagrange equations, and they are going to serve as the equations which will lead to the equation of motions. So one thing which we saw on Monday is that if we identify this Lagrangian or this function L as the difference between kinetic energy and potential energy, we could then derive Newton's equation of motion. So that's an extremely powerful way of actually deriving equations of motions. And when you are going to take more advanced physics courses, you are going to see that you can recognize a quantity like the energy as something which is given by this function S, and then you can optimize the energy integral, and from that one you can actually derive the equation of motion. So let's look at an example. So the first example we are going to look at is to show that we can use variational calculus to show that the shortest distance between 2 points is a straight line. So this is the shortest path between 2 points. And these points are points which are really, and now we are not going to deal with time, but we are now going to deal with x and y. So these are just 2 points in x1 and y1, and another point which we just call x2 and y2. So if we make a plot now, so now I'm not dealing with time, but I have x on the x-axis. So I start with a point x1, I end at a point x2, so this is our x-axis. I have my y-axis here, a y1 and a y2 here. And we start in this point, and then we end in this point up here. And then there's a path here. And we know by experience that the shortest path between these 2 points is a straight line. But let's prove that mathematically. So what we're going to say now is that there's a small piece here, which we're going to call d of s. And this d of s is now going to be given by first of all, we are going to define a line. So this is the length between x1 and x2. And this is us integrating up these small distances, d of s. And we are going to define this d of s in the same way as we will define a radius. So it's going to be given by dx squared plus a dy squared. That's the way we're going to define this small line element d of s. So you could now think of us looking at a specific point along this line, and the distance from an origin to that specific point would typically be x squared plus y squared. So we define this d of s, which is the value of this specific line segment, as dx squared plus dy squared. I hope it sounds logical what we're doing here. And you may have seen this example in mathematics courses. Have you seen that demonstrated in a math course? So some of you have seen it. Okay, so let's, for most of you, it was actually for me as well, it was not familiar because it depends on the kind of math courses you've taken. But let's now show that this is actually the case. So when we do this, the thing we are going to do now is to do a slight rewrite. So dy is now given by dy dx, multiply with dx, nothing exciting here. And this is going to be given by y prime. So this is a derivative. So the y prime is a derivative of y with respect to x. That means that I can rewrite ds here in terms of, if I'm now pulling out x dx squared, I have 1 plus 1 prime, the second derivative squared, multiplied with d of x. So this is just a rewrite of this tiny, tiny line element in terms of just one of the variables, which is now d of x. And then I have the derivative of y with respect to x. So what I want to show now is that y as a function of x is given by a straight line. Then the next thing which I need to do now is to look at my L, which is actually the same as this quantity S, the action as we called it, except that now instead of having the Lagrangian, we have another function, and this is a function of the derivative of y and of x. So we are now going to optimize this quantity here, of y, and this is the derivative with respect to x of dx. So that's the quantity we now want to optimize. And we're going to show that this L is now going to be proportional with a straight line. That is the mathematical object which optimizes the distance between points x1 and x2. We know that already by experience that this has to be a straight line. So if we now use the Euler-Lagrange equations here, what we have then, with respect to y, we have a d of y minus of d dx. Previously we had time because we were looking at something which depended on time, but now it's something which depends on a displacement x. And then we have a dy prime. This is the derivative of y with respect to x, and this has to be equal to 0. The other quantity, so when we do these calculations here, what we end up with, if we now define a function, let's call just this function f as 1 plus, so we are optimizing our function here of y, the derivative of y squared. So when we now calculate the derivatives here, and we also note that dl dy is equal to 0. So we have dl of dy is equal to 0. And in our case, this L, which we had previously, is actually given by this function, which we now have called f. So L is no longer the Lagrangian, but it is a function which we label f, which now corresponds to this tiny displacement d of s. So in our case, what we have is that df of dy, there's no y dependence, that has to be equal to 0. And then we see that the other quantity which we need to include now, and this is going to be df of dy prime. This is also a quantity which now, since this one is 0, that simply follows from the Euler-Lagrange equation, that means this equation here, then it simply follows that this one has to be equal to 0. Now, what does that mean? Now, that means that if I now integrate, if I take this equation here and I integrate with respect to x, this means that the derivative of f with respect to the derivative of y, that has to be equal to c, which is a constant. Does that sound logical? So because now the only thing I have is a dependence on the derivative of y as a function of x. And when I use the Euler-Lagrange equation, where I change L to the function f, which we are studying, then what follows from that is that the derivative of this function with respect to the y derivative has to be equal to a constant. Now then, the next thing is to simply plug in the function again. And we know that if I take the function and I calculate the value of that, so we know that f is now given by this square root of 1 plus y prime squared. If I take the derivative of that quantity, what we get then is that I have y prime divided by 1 plus y prime squared, and this is equal to c, and it's the square root of that, like this. So the next thing I do now, I square both sides. So if I square both sides, what we're going to get then is a y, the derivative of y squared is equal to c squared of 1 plus y derivative squared. And that means that what I get then is, if I now shuffle over the y prime terms, and I have a terms in terms of c squared, so I isolate the y prime terms. So what I get is a y prime of 1 minus c squared is equal to c squared. That means that y prime squared is now simply equal to a new constant, which is the same as c squared divided by 1 minus a constant c squared. Now, if you now look at this one, what we have is that y prime is plus minus the square root of this quantity d. And now from that one, what can I say about y itself? So d is a constant, and we can just label this one and we just call it for a new constant. So let's just call this for a new constant a in order just to simplify life here. So if that is a constant, what is y like? If I integrate up with respect to x, that becomes a straight line. So just a times x plus a new constant. So that means from this one, what we can show then is, so when I integrate up again, then I have that dy d of x is simply equal to a. And that means that my y then of x has to be equal to a times x plus a new constant b. And that is a straight line. So what we have used now is to set up a function for a line segment. We integrate up all this line segment to get the full line. So that's the quantity which we express as an integral. That's the full line. And then we have a mathematical expression for this line segment. And then we optimize this function. And then we can show that the shortest distance between 2 points is a straight line. So that's one of the ways of showing that, by using variational calculus, where we now have rephrased the whole line as a sum over all the tiny line segments. And then we let these line segments go to 0, and then we integrate up. So we have expressed the distance between 2 points in terms of an integral, where that integral is just the collection of the infinitesimal small displacements. So this is an example of you using the variational calculus to show something which is pretty obvious. Now, one of the things which becomes interesting for us now is that we can actually use this variational calculus with a Lagrangian to show that energy is conserved given a specific form of the potentials. So the next example is about energy conservation. So let's take a look at that. So what we have here is a straight line. I guess nobody doubts that. And this is what we wanted to show. So let's use the same formalism now to show energy conservation. So this is going to be an example 2 here, and that's energy conservation. So now we start with the Lagrangian itself, and this is normally reserved, this function L, to be a function which would typically depend on the position, the velocity, and time, and that's given by 1/2 of m. So let's assume that we have only one object, and now we are making a further assumption. So this object has mass m, it has a velocity v, and there is a potential which now depends only on x. So here we've made an important assumption that the potential itself depends only on the position itself. And we know already from that if we have a position-dependent potential, that normally, if the curl is 0, then normally we should actually get something which conserves energy. We can have potentials which depend on velocity and on time as well. So when I irradiate a quantum mechanical system with a laser pulse, that is something which is time dependent. And that would introduce a time dependent potential. But if you're thinking of the motion of an object in a gravitational field or a Coulomb field or something like that, that is a quantity, a potential, which depends only on the spatial degrees of freedom. But keep in mind that you can encounter potentials which can depend on velocity and on time as well. So we can have a time-dependent potential which acts on the system in only a specific amount of time. So let's now see that we can actually conserve energy or show energy conservation. So we are now going to set up some of the basic equations again. So we have dx dt is equal to v. We define this action S of t1, dt2, of L, of x, of v, of t, of dt. Now, there's something in physics which we call a stationary quantity. So have you encountered this topic, stationary quantity, before in physics, this concept? So if you think of the word stationary, a stationary quantity, what do you think that actually means? Yeah?
Like not changing?
Not changing, as a function of
time.
So when we say a stationary quantity, we mean normally that this is a quantity which would not change as a function of time. So if I take the time derivative of s, then this function should not change as a function of time. So it should stay the same value. And we know that the energy is actually, if you have an energy conserving force, then we know, and you have seen that in the different homeworks and also in the last midterm, that energy is conserved. So let's look at the energy conservation. So if we say that this is a stationary quantity, what this is going to mean for us is that ds of dt is equal to 0. Now that means in turn, when we look at this integral, which we have, since the only quantity which depends on time is the Lagrangian itself, that means that what we also would have then is that dl dt is going to be equal to 0. So suppose you didn't know anything about stationary quantities and you just ask yourself, what is the time derivative of this quantity? We can obviously ask, when we have minimized something, so suppose you're looking after the energy minimum of a quantity, and then you ask yourself, does this situation change over time or not? That's a very legitimate question because you would like to know whether you're staying in the same state or not. So let's just say that you want to take the derivative with respect to time. So if we do that now, what we need is some small mathematical manipulations. So we are going to need, in order to do this, we need just some few manipulations here. We need to take dl, since we have a dependence on time now for the velocity and the position. So we need actually dv dt. And we need also something like this. Dx, this is the partial derivative, and then I have a dx dt. So this is a quantity which we need. We also have the Euler-Lagrange equations. So, which says simply that d of L of dx minus d dt of dl of d of v is equal to 0. Now, the quantity which we have put in here, this first quantity, this is now going to be the time derivative of the, or it's going to represent the time derivative of the Lagrangian. So if we look at this equation, and we also look at this equation here, we can rewrite the equation for the time derivative in terms of a d of L of dt, and this is equal to d of L dv. So what I'm using now is actually, I'm setting in the equation for dl dt, so I'm taking the velocity dependence, and then I know that the velocity, the derivative of the velocity is nothing but the derivative, the second derivative of the position as a function of time. And then I get plus, and now I'm going to use the Euler-Lagrange equation. So I'm going to replace this one with a quantity which you see here. So if I do that, we get a new term, which simply goes like d dt of d of L of dv, and this is multiplied with dx dt. Now, if I do collect these terms now, you can easily see that you can rewrite this in terms of a d dt, and then we can rewrite that as a d of x dt over dl of dv. So these are just manipulations with derivatives, where I now wanted to introduce the velocities and the positions because we know that these quantities depend on time. This quantity is again nothing but us taking d dt, and we know that this one is equal to the velocity, and then I have a d of L of dv. And this is equal to d of L of dt. And if I then collect this term on the right-hand side to the left-hand side, then we can simply rewrite everything in terms of a strange function here, which looks like v d of L of dv minus L equal to 0, whatever that means. Now, this doesn't look like I have showed anything except some few mathematical manipulations. So what I'm going to plug in now is the expression for the Lagrangian in terms of the velocities and the potential. So observe one thing now, that in this derivative, there is no dependence on the potential or on x. So the potential depends only on x now. So just pay attention to that, because this is what is going to give us energy conservation. So the thing we need to observe is first, if we go back a little bit, one of the basic, we made an assumption here that there is no dependence on velocity, no v or t dependence. So this is an important constraint which we put on the potential energy. So if I now go back to what we had, then we have a Lagrangian which is given by 1/2 of m times v squared minus v of x. So this means that when I now take the derivative of the Lagrangian itself here, so this is actually a crummy way of writing this uppercase L. So this should be like this. If I now take the derivative of this quantity, so what I have then is actually a d dt, and now I plug in the derivatives. So when I take the partial derivative with respect to v, I get n times v, but then I have a v in front here, so that gives me a v squared, and then I have minus the half the kinetic energy of v squared, so this is half the value, and then I have minus the potential, but there is a new minus, so this becomes plus v of x, and this is equal to d dt. And what would this one be equal to? If you now do the summations here, what do we get? If you add n times v squared minus 1/2 n times v squared plus the potential energy, do you see immediately what that leads us to? That's the energy. So what we have showed here is actually energy conservation. Without going through all this discussion about conservative forces, we actually show that energy is conserved by just looking at the Lagrangian and rewriting these Euler-Lagrange equations and simply asking ourselves, what happens if I take the time derivative of this Lagrangian? So when I take the time derivative of this Lagrangian, or the action itself, which we want to optimize, then what we are saying is that this leads to conservation of energy. So that's another way of actually showing energy conservation, which does not start with the equations of motion or the force itself. It actually starts with the kinetic energy and the potential energy. So that's an extremely powerful way of obtaining what we have seen before when we looked at the curl of the force. So here you actually have an explicit expression for energy conservation. And this is equal to 0. So energy conservation, energy is conserved. So in a way, what we are doing here at the end of the semester is to collect many of the things which we have done with standard Newtonian mechanics, but we are trying to reformulate them using the calculus of variations. And that's a very powerful mathematical way of describing physical systems, which you are going to encounter in many, many different physics courses. Okay, so let's look at the next example. So one of the things we are going to look at is the example which we have been dealing with again and again in chapter 8. And when Taylor derives these equations in the textbook, what the author actually does is to start with the Lagrangian formalism. Whereas what we did, since we hadn't introduced the Lagrangian formalism first, was actually to start with standard Newtonian mechanics. And we started with the forces, and from the forces, we were able to derive the equations of motion. So let's now simply look at what we had done in chapter 8 and what actually Taylor is doing. So this is a two-dimensional problem. So we have the derivative of x, we have y. So this is something which now depends on two spatial degrees of freedom. And this is a quantity which we then would transform in terms of something which depends on the radius and the angle phi. Now, the Lagrangian itself, this function, when we made the transformation to polar coordinates, what we had then was the time derivative of the radius, so the radial coordinate, so what we normally call the radial velocity. And then we had the angular velocity, which had a phi dot squared. And then we have in addition a potential energy, which we may or may not specify to have an angular dependence. Now, when we looked at the gravitational force, and this is a case of most of the more famous physics courses, there is only a dependence in most of the forces which we know from nature, and there's basically no experimental deviation from that. There's essentially a dependence on the absolute value of the distance between two objects which interact. So we say normally it's isotropic in space, and there is no dependence on the angles. But it could happen that you have a dependence on the angle. So let's just leave that potential as something which can depend on the angle phi as well. Now, in chapter 8, we looked only at potentials which depended on the radial distance between two objects. So let's leave it a little bit more general and see what kind of equations of motion we can extract then. So if we take the R equations, what we need to do then is to calculate or set up the Euler-Lagrange equations with respect to the radial derivative. And this is minus d dt of d of L of d of R prime. So if we now look at the equations here, we know that there will be a dependence on the potential energy. So if you look at the explicit R dependence, this quantity here, that R dependence is something which we only will have from this quantity. Then the dependence on the radial velocity in this term here is something which we would get here. Now we have to be a little bit careful as well, because there is a further term in our case. So there is a radial dependence on this term as well. So we have a radial dependence in this term here, which comes from here and comes from here. And then we have a dependence on the radial velocity, which comes from this term here. So the function which you see here is the kinetic energy, which we some weeks ago transformed from Cartesian coordinates to polar coordinates. That's just a plain transformation of these quantities, which we went through some time ago. Now, if I now take and collect these different terms, then what we will get from the derivative with respect to the radius r, what we end up with now is an equation which is going to run like n times r, and then we're going to get a phi dot. We are going to get a derivative with respect to v and with respect to r, minus dv dr. And this is going to be equal to n times the second derivative with respect to r. And this term which you see here, the last term, this term here, that comes actually from this one. So we actually have this one has to be equal to 0. So I take the derivative of this quantity, so this quantity here, that gives me this term. There's a factor of r dot squared, and I have a factor of 1/2. So that simply gives me that one when I move that to the right-hand side. And then I have a term from the kinetic energy, which is this term, which now gives me this one. And finally, there is a term from the potential, which simply gives me this one, minus dv d of r. And I haven't specified whether the potential depends only on the radial coordinate or on the radial coordinate and the angle. Now, the quantity which we have here, this is nothing but the radial force, which we had as the gravitational force in chapter 8. So when we collect everything, what we have then is that the acceleration, the radial acceleration, is then simply given by r of phi dot squared, which led to the angular momentum, plus a term which we call f of r divided by the mass of the particle. And this is the equation which we could solve analytically if we plugged in the gravitational force. So this is an equation we have seen before. So we can derive that one with basically much greater ease if we have already made the transformation to polar coordinates. Then we can just use the Euler-Lagrange equation and get the equation of motion. So this is actually Newton's law for the radial degrees of freedom. Now, the next thing we need is the phi equations. And we haven't said anything about the potential itself. So what we are going to need then is to set up d of L of d phi is equal to d dt of d of L of d phi dot. So there's a dot here. So this is the equation we need to set up now. And one intermediate thing we need to keep track of, when we look at the derivative of the potential, that means the force, the gradient of the potential, in radial coordinates, that is going to be equal to dv of d of r. We have the unit vector in the r direction. And then when we look at the transformation from Cartesian to spherical to polar coordinates, what we have is an r of dv of d phi multiplied with the unit vector in the phi direction. So this is a corresponding thing which we would have if we were dealing with this in Cartesian coordinates. That's a transformation of a gradient from Cartesian to polar coordinates. I guess you've seen something like that before. Now what we can define then is a quantity which we are going to call f of phi, and that's going to be the potential minus d v d phi. And actually this is something which we're going to link with that quantity. So when I now plug in the Euler-Lagrange equations and then look at my Lagrangian, I know that this one is going to give me a term which is proportional to phi derivative. So if I look at the equations now, what we will get is an equation for the force. So notice as well that there's a 1 over r here. So if I want the force, what I need then is r of f of phi. And this is going to be equal to d dt of n of r squared multiplied by phi. Now what happens if v, instead of being a general function which now only depends, on both coordinates, only depends on r? So what happens with f of phi? Suppose we now go back to what you have seen in chapter 8. So I'm actually sneaking in some kind of repetition here. So what happens if we now have a potential which depends only on the radial distance and not on any angle? What is the derivative of that quantity with respect to phi if it does not depend on phi? It's zero. Again, when I have this kind of tone in my voice, it's often I'm looking after the roundest numbers which exist. So this is this potential. Maybe that was an offensive question actually to ask, something which is pretty obvious. Okay, so in our case, this is actually equal to 0. So f of phi is equal to 0. Now, if you now look at what we have here, and let me see if you remember some of the things which we have discussed. So this obviously means that our right-hand side, no, sorry, the left-hand side, I still have to learn the difference between right and left. The left-hand side is 0. So what we have then is that this term is conserved. M times r squared times phi dot is a conserved quantity. Now, do you remember what that quantity was like? This quantity is a quantity which we calculated and we defined, and you've been playing around with it in many times, and you're actually using that in homework number 9. So this specific quantity which you have inside here, so this means that this quantity is conserved as a function of time, right? It doesn't change. If you then look at this other term which you have up there, it says R times the force. And now this is written in polar coordinates, so you may not recognize it immediately, but we have a quantity which is given by R times the derivative, cross the derivative of the angular momentum, the linear momentum. Do you remember what we called that quantity? We had it back in the beginning of the semester. Begins with T. The torque, right? So what we have on the left-hand side is actually the torque. And what we said now is that the torque is equal to 0. And if the torque is equal to 0, the torque is defined as the time derivative of angular momentum. So what we have here is that if the potential, so if you're so lucky in your physics examples or the cases you're looking at, that you have a potential which depends only on the spatial degrees of freedom and the distance, the relative distance between two objects, or just the absolute value of the coordinates, then angular momentum is conserved. So this is another way of showing conservation of angular momentum, but with you starting with the form of the potential. So if somebody gives you a potential which depends only on the relative value or the absolute distance between two objects, then you could say, using the Lagrangian formalism, that angular momentum has to be conserved. And you can see that easily if you make the transformation to polar coordinates or spherical coordinates. So what we have seen here is that actually angular momentum is conserved. So this is the same as saying that d dt of L is equal to 0, because L is actually given by this quantity here. So angular momentum is conserved if we made these assumptions. Now what I'm going to plug in now is our next step, and that is variational calculus and constrained motion. And this is also a case where the Lagrangian formalism is really at its best. So what you will see now, we're going to take a kind of top-down approach first, and then we are going to look at more of the mathematics next week. But what we can do is, by a very small change in this Lagrangian, we can derive the equations of motions when you have a constraint on the motion. So let me show you a very classical example. So suppose now that we have a system in 2 dimensions. So we have the x-axis, y-axis, and then we have a plane, and we have an object which is sliding down on this plane here. And then this plane has an incline with an angle of alpha. And in this particular case, there's only the gravitational force which acts, Fg. We are taking away friction, so we're making life easy for ourselves. And that's given by m times g. And this object has a mass of m. So this is an example of a constrained motion, because you're forcing the object to slide on this incline only. You can obviously ask yourself what happens when we are going to leave the incline. But let's now suppose that you're forced to move along this incline here. So if you want to find a mathematical expression for the constrained motion, what kind of, in which way would you like to, could you phrase the dependence between the angle alpha, y, and x? So if you look at the expression here, so we want now to find a constraint on y and x, because this object is moving in 2 dimensions. So it's not like me who moves only 1 dimension, but this actually moves in 2 dimensions. And there is a constraint here, that there is an angle alpha. So if you want to phrase this constraint mathematically, what kind of function comes to your mind? There's a famous trigonometric function you could use here. Tangent, exactly. Excellent. So we will constrain the motion now, and this is where we're going to stop today. So the constrained motion is simply that y is equal to x times tan alpha. This is going to affect the equations of motion. And these are the equations which we are going to look at a little bit on Friday, but then we are going to look more at the mathematical details on Monday and Wednesday next week. And then Friday next week, we are going to summarize and discuss the final midterm and all other practicalities with the rest of the semester. But this is the kind of constrained motion which we can have, the constraint of the motion. And from that constraint, we can use the Lagrangian formalism to derive the equations of motion. And that's pretty cool. Any questions? Yeah? I have to get them. Yes. So, for those of you online as well, the final exam is exactly as the midterms and the homeworks is take home. And I also thought of suggesting the times we could meet in the finals week. So you will probably have tons of questions. So we can have office hours, times when we meet and discuss, and so on and so on. Okay, guys. See you on Friday. Let me just switch off the recording.